morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. In the today's lecture, we are going to learn one of the topic in time-varying fields or electromagnetic fields as important one called displacement current followed by displacement current density. Then what is the inconsistency in Amperes Circuit Law? Okay. So before going to discuss about this inconsistency which is exist in Amperes Circuit Law, let me introduce the topic called displacement current. Right? So from this displacement current, generally we use the notation for current as I. And current density means with a J we are going to represent it. And JC or JD. There are three current densities are there according to the different variations in the currents. So first two JC and JC we have discussed in the static, electric as well as magnetic fields. So these two JCs means the first JC stands for here convection current density. Convection current density. Whereas this JC stands for conduction current density. Right? There is a difference between this JC and JC where convection current density is given by JC equal to rho V into U, and according to conduction current density JC is given by sigma into E, where sigma is said to be conductivity of the material and E be the applied electric field. Generally, we used to consider the notation for electric field intensity as E in the electric fields. Now, similar to that of these two, convection current density and conduction current densities, we have another term current density called JD. So D stands for here displacement current density. So this displacement sometimes is called as distance. Means in order to measure the distance, we need to know two reference points. Right? So according to that, the current density is given by here displacement current density and it is denoted with JD. D stands for displacement. Right? So in order to derive the mathematical equation for the displacement current density as JD, we are first recollecting what is the basic Amperes Circuit Law which we have already learned in the case of magnetostatic fields. Right? So that is for electrostatic electromagnetic fields, the del cross H is given by J, where H is the notation for magnetic field intensity and J be the conduction current density. So this already we have derived in the case of static magnetic fields. There we have considered the fundamental law is known as Amperes Circuit Law, or simply it is also called as Amperes Law. Now according to that static electromagnetic fields, we just derived the point form or differential form of the Maxwell's equation for the static magnetic fields is del cross H is equal to J. Right? Now from this mathematical equation, we just consider the one of the vector identity is called as the divergence of the curl of any vector field is identically equal to 0. Means del, the divergence is represented with del dot. Divergence of curl we are representing with del cross of any vector field where H is always a vector. Hence, del dot del cross H is denoted with here is divergence of the curl of any vector field is identically 0 according to the vector analysis. Now, del dot del cross H is equal to 0 is the according to the vector analysis. Now here, if you apply, consider the first equation as the static magnetic fields Amperes Circuit Law, that is del cross H is equal to J. Now consider this as one of the equation. Then for that equation, if you apply both sides divergence to that, then del cross H equal to J becomes del cross H equal to J becomes, if you apply both sides divergence, then it resembles here del dot del cross H is equal to del dot J. Right? But according to the vector analysis, here divergence of curl of a vector field is nothing but 0. Right? If this is 0 means LHS part of this is equal to 0 means automatically RHS part of that must be equal to 0. Hence del dot J is equal to 0 according to the application of divergence of the curl of any vector field from the analysis part of vectors. Right? Now, del dot J is equal to 0, which we have got from the vector analysis, but according to the continuity of the current equation. So, this also already we have studied in the case of static magnetic fields, that is according to the continuity of the current equation, or simply we'll call it as continuity equation, that is given by here del dot J is equal to minus of dou rho v by dou t, where J is said to be conduction current density and rho v be the volume charge density. Right? So the relation between conduction current density and the volume charge density, which should be expressed in terms of continuity of current equation, or simply continuity equation, means del dot J is equal to minus dou rho v by dou t, which is not equal to 0. Why it is not equal to 0 means, according to the static magnetic fields, we have got the equation for the continuity equation as del dot J is equal to minus dou rho v by dou t, but according to the vector analysis here, del dot del cross H is equal to 0 resembles that del dot J is equal to 0. So if you observe, these are the two equations. Here del dot J is equal to 0. Now from this equation, del dot J is equal to minus dou rho v by dou t. So if you observe these two equations, there is a confliction, or there is a difference between that vector analysis part and according to the continuity of the current equation. To satisfy or to resolve that conflict which is exist in these two cases, we are going to add one of the term to the Amperes Circuit Law as JD, where JD is said to be displacement current density, which is added to the conduction current density. Hence, the modified form of the displacement or Amperes Circuit Law is obtained in the case of time varying fields or electromagnetic fields is del cross H is equal to J plus JD, where H is always a vector. Right? So del cross H bar equal to J plus JD, where J is said to be conduction current density and JD be the displacement current density. So to resolve this conflict which is exist between 1 and 2, we will add one of the term called displacement current density to the RHS part of Amperes Circuit Law. Then it becomes del cross H bar is equal to J plus JD. Right? Where JD is given by displacement current density, means it is a rate of change in which is occurring in D called electric displacement. It is also known as electric flux density. So generally electric flux is measured in coulombs, and this flux density can be measured in coulomb per meter square. Flux per unit area. Hence the unit becomes coulomb per meter square. Okay. So where JD is said to be displacement current density, and mathematically we can write the equation for that is JD equal to dou D by dou T. Right? So if you substitute in place of this JD as dou D by dou T in this equation, then del cross H bar equal to J plus dou D bar by dou T. Right? So J is given by here conduction current density. According to that, the formula is J equal to sigma into E. So del cross H bar is equal to J plus dou d bar by dou t. Now if you substitute here again the divergence on both sides of this equation, then it becomes del dot del cross H bar equal to del dot J plus JD. Right? So del dot J plus del dot JD. So del dot del cross H bar is according to the vector analysis if this is equal to 0, but from this we are going to get del dot J plus del dot JD. Now from these two we are going to get del dot JD is equal to minus del dot J, which is not equal to 0. So this is the way the conflict which is occurring between the vector analysis of the Amperes Circuit Law and according to the continuity of the current equation to be evaluated or eliminated from this modified form of the Amperes Circuit Law is del cross H bar equal to J plus dou d bar by dou t. Right? So the term JD is nothing but dou d bar by dou t is known as displacement current density. So this is the one of the modified form of the Amperes Circuit Law which is obtained in the case of time varying fields as del cross H bar equal to J plus dou d bar by dou t is known as point form or differential form of the Amperes Circuit Law. If you want to write the equation in terms of integrals, then both sides if you consider integrations, then integral L H dot dl is equal to integral S J plus JD dot ds. Why? Because in order to get this one, we are going to apply the Stokes theorem, and it also gives the relationship between line to surface integrals. Now, if you convert that one, this is the integral form of the Amperes Circuit Law, which is expressed in time varying fields or electromagnetic fields. Okay. So this is what about displacement current density, and JD is said to be displacement current density and ID is given by here displacement current. Generally, the notation for current is represented with I and D stands for displacement. Okay. So after defining the displacement current or along with the density called displacement current density, one of the drawback which is exist in Ampere's law is known as here. There is an inconsistency in Ampere's circuit law that how we are going to eliminate we'll come to know with the help of this simple diagram. Right? So firstly, consider the two images. In the two images, in the first half circle, the total planar surface area is represented with S1 and the current which is flowing through that it is represented with I, and similarly throughout this path, Amperean path. Why? Because we are analyzing the Ampere's law, hence the surface is represented as Amperean surface or path. And consider the another diagram which is means the circle is divided into two semicircles, hence the surface is divided here. In the first case, it should be represented with S1 and in the second case, it is given by S2. And throughout this path, the current, throughout this path L, the current I is uniformly distributed. When you consider into the semicircle case, there exists a conflict, means there is a mismatch current, means the current which is not flows through this S2. Why? Because what is that reason? What is that drawback which is exist in the second region? Means firstly, without the term JD, without considering the term JD, what is this JD here? Displacement current density. So without the term JD, considering the propagation of the electromagnetic waves would be impossible. Why it is impossible? Means firstly, at low frequencies, JD is usually neglected compared with the G. Why? Because at low frequencies means generally we know that the JD is represented as in the mathematical equation as dou D by dou t. Okay, dou d bar by dou t. And if you substitute here in place of this d bar by epsilon and E bar, then dou by dou t into epsilon into E bar. Now if you consider epsilon as a constant, dou E bar by dou t. So for all the time varying fields, the partial derivative means the changing term, that is dou by dou t, is replaced by j omega. Hence, the jd term can be represented as here jd equal to j omega epsilon into E. Or if we replace this epsilon into E by d, that is given by here j omega into d bar. So, where omega is said to be angular frequency, and here if you consider omega equal to 2 pi f, right? So, at low frequencies means if omega equal to 0 or f equal to 0. If f equal to 0, omega equal to 0. Now, if you substitute here, jd becomes omega by 0, then jd becomes 0. Hence, at low frequencies, jd is usually neglected. Why? Because it is very, very less, hence, and it is compared with j. Hence, so based on the displacement current density, we define the displacement current, and it is given by the mathematical equation as id equal to integral s jd dot ds. And we know that the jd is defined as with respect to the displacement, electric displacement, as integral s dou d bar by dou t into ds. Okay. So, in general, we know that the current is expressed in terms of current densities, means integral s j dot ds, where I is the notation for the current and j be the j significance represents here current density. So, I equal to integral s j dot ds. Depending upon the current density we have considered, whether it is convection current density or conduction current density. Now, in this case, it is displacement current density. We are representing the subscripts as C or D sometimes. Hence, now we are discussing displacement. Hence, the notation is given by here id equal to integral s jd dot ds, which is equal to, we'll replace jd by the formula dou d bar by dou t. Hence, id equal to integral s jd dot ds, which is integral s dou d bar by dou t into ds. Right? Then upon applying means applying an unmodified form of Amperes Circuit Law to a closed path L. So previously we have seen the two diagrams in the first circle. The full circle, in the first figure it resembles integral L, closed line integral L. Why? Because that path is to be considered as here closed. Hence we are representing the circle with the integration as closed circle L h dot dl is equal to integral s j dot ds. So this is the equation for I, and which is equal to I enclosed. According to the Amperes circuit law, we know that closed line integral L h dot dl is equal to the net current which is enclosed by that path is given by here integral L h dot dl is equal to I enclosed. So throughout that path S1 here, the path is L and the surface we have considered there as S1, hence J dot ds. Throughout that surface, that charge is, that current is uniformly distributed, hence I enclosed is considered as I in the first case of the previous figure. Now coming to the second figure. Now this is the case closed line integral L h dot dl is equal to, now here's the surface is to be considered as S2. Hence integral S2 j dot ds, which is nothing but I enclosed is equal to 0. So there is a mismatch which is exist in the figure B, that is second figure in the S2 case. Then net current which is enclosed by that surface S2 is equal to 0. So in order to overcome this one, or in order to overcome this conflict, we are modifying the Amperes circuit law by adding displacement current. Then this is the way the inconsistency which is exist in the Amperes circuit law is to be eliminated by adding displacement current to the respective surfaces. Hence, no conduction current, that is J equal to 0, which is flows through S2. Hence, I enclosed is equal to 0 in this case. Okay. Then, to resolve that conflict means if you consider in the first case closed line integral L means the surface we have considered as S1. This is the case the current I enclosed is equal to I in the first case. If we consider the second case as S2, then I enclosed is nothing but here 0. Right? So in the first case if we observe the total current as I, and in the second case if we observe the total current is 0. So in order to produce the current which is exist in the path 2 is also which is equal to I. So to resolve that conflict we need to include the displacement current in the Amperes Circuit Law. Hence integral L H dot dl is equal to JD dot ds. Why? Because according to the Amperes Circuit Law, integral L H dot dl is equal to I enclosed. Now, I is nothing but here according to the current density, that is expressed as integral S JD dot ds. Hence, in place of I, if you substitute here as integral S JD dot ds, then integral S JD dot ds is nothing but here I enclosed. Now, if you substitute JD by dou D by dou T is the mathematical equation. JD equal to dou D by dou T. Now, JD by if you substitute, then integral S JD means dou D bar by dou T into ds. Now, if you consider that in the inside the integration, the term is considered to be as here dou by dou T. If you take this into out of the integration, then it becomes d by dt integral S d bar dot ds. So here d bar is nothing but electric flux density and it is also called as electric displacement. Right? So according to the Gauss Law, what it states that Gauss Law means the flux passing through any closed surface is nothing but d dot ds is nothing but the total charge which is enclosed by that surface, means psi is equal to q enclosed according to the Gauss Law. What does the psi resembles? Means the flux which is passing through any closed surface. Hence, electric flux is represented with psi and the flux density is denoted with d bar. Hence, the psi is replaced by here integral S d dot ds, which is nothing but q. Right? So if we replace this total term by q according to Gauss Law, then dq by dt. So what is this dq by dt? Change in the rate of change of charge which we have considered with the fundamental definition of the current I. Hence dq by dt is replaced by here I. Right? So according to the fundamental definition of a current, it is given by rate of change of charge or charge per unit time is given by the unit current, that is I equal to dq by dt. So this is the way by adding displacement current density, then in path 2 S2 surface S2 also containing the current as I by inserting the JD into the conflict which is exist in the Amperes Circuit Law. So this is the way the conflict which is or inconsistency which is exist in the Amperes Circuit Law is eliminated by adding displacement current in that particular case. Hence, closed line integral L H dot dl is equal to I according to the Amperes Circuit Law. Right? So this is the inconsistency of Amperes Circuit Law is eliminated, and this inconsistency is eliminated by adding displacement current and along with the density we have analyzed. Right? So now Maxwell's equations or the final forms of the Maxwell's equations which are to be in time varying fields or electromagnetic fields. Right? So in separately we have evaluated static electric and static magnetic fields, Maxwell's equations. So under static electric fields, first law we have got as according to Gauss law, that is integral S d dot ds is equal to integral V rho V dV is the Gauss law which is to be obtained in the case of static electric fields. And one more is Maxwell's law which is exist in the electrostatic fields as closed line integral L E dot dl is equal to 0, or from this del dot d bar equal to rho V. Now from this del cross E bar equal to 0. So these two are called point forms or differential forms of the two Maxwell's equations which are evaluated in the electrostatic fields. Now del dot d bar equal to rho V and del cross E bar equal to 0 are point form or differential form of the first two Maxwell's equations which we have learnt in the case of electrostatic fields. Now coming to the magnetostatic fields. In the magnetostatic fields also we have got two Maxwell's equations. One is del cross H bar is equal to J as the point form, or integral form means closed line integral L H dot dl is equal to I enclosed, or integral is J dot ds. Similarly, fourth Maxwell's equation has del dot B bar equal to 0, or integral form means closed surface integral S B dot ds is equal to 0. So these are the four Maxwell's equations which are already learned in the case of static electric as well as static magnetic fields. Now out of all these four equations, two of the equations are to be modified in the case of electromagnetic fields or time varying fields. Now hence all these static electromagnetic fields Maxwell's equations are to be finalized in the case of time varying fields or electromagnetic fields is given by here. First, differential form or point form, and the second case as integral form, and the remarks means in which law it is to be derived or what is the drawback which is exist in the particular laws, right? So first law in the Maxwell's equation of time varying fields or electromagnetic fields, or first is given by del dot d bar equal to rho V and closed surface integral S d dot ds is equal to integral V rho V dV, and this is to be obtained from the Gauss law, right? According to psi equal to q enclosed, the psi must be expressed in mathematical equation as in the integral form of that equation to be closed surface integral S d dot ds is equal to integral V rho V dV. Now second Maxwell's equation to be considered in the case of time varying fields as del dot B bar equal to 0, or integral form means closed surface integral S B dot ds is equal to 0. And the remarks or the statement is given for that is non-existence of isolated magnetic charge. Means this is the statement is explained already. We have learnt in the case of magnetostatic fields. Suppose if we have a magnetic bar which is having two poles as north and south, if we cut this magnetic bar into two parts, again it is going to form the two poles as north and south, like this. Again if you separate these two into two, again it is going to form north, south, like this. Means we cannot separate the magnetic bar into two. So, means non-existence of isolated magnetic charge. Means isolated magnetic pole cannot be exist in that particular closed surfaces. Hence, del dot B bar equal to 0, then closed surface integral S B dot ds is equal to 0. Right? Now, coming to the third Maxwell's equation is del cross E bar equal to minus dou B bar by dou T. And according to the static electric fields, here del cross E bar equal to 0, and this is to be modified according to the time varying fields as del cross E bar equal to minus dou B bar by dou T, and the integral form is closed line integral L E dot dl is equal to minus d by dt integral s b dot ds. So this is the equation is said to be differential form, or here it will be integral form of the Maxwell's equation, which is derived from the Faraday's experiments. And the fourth law is Amperes Circuit Law, which should be written in differential form as del cross h bar is equal to j plus dou d bar by dou t, and integral form means closed line integral L h dot dl is equal to integral s j plus dou d bar by dou t into ds, where j is said to be conduction current density and it is given by sigma into E bar, and dou d bar by dou t is said to be displacement current density, and that is the modified form of the Amperes circuit law, which is to be obtained in the case of time varying fields or electromagnetic fields as del cross h bar is equal to j plus dou d bar by dou t. Right? So these are the four Maxwell's equations which are to be finalized in the case of time varying fields or electromagnetic fields. Right? So basically there are four Maxwell's equations. The whole universe is working under all these four principles. Right? So the flux which is passing through any closed surface is nothing but the charge which is enclosed by that surface is given by according to the Gauss theorem, that is psi equal to q enclosed, and it is applicable only for the symmetrical charge distributions case only. And the second one universally, that is del dot b bar equal to 0, means magnetic monopole does not exist in any closed conducting surfaces. Hence closed surface integral s b dot ds is equal to 0. And according to Faraday's experiments, del cross E bar equal to minus dou B bar by dou T. And according to the modified form of the Amperes circuit law, that is the equation is del cross H bar equal to J plus JD, where J is said to be conduction current density and JD is displacement current density. Right? So these are the four Maxwell's equations which are to be finalized in the case of time varying fields or electromagnetic fields. Okay. So now, next one is conditions at a boundary surfaces. What are the different boundary conditions which are exist in the case of two different media? This all we have discussed in the case of two separate cases as boundary conditions between two dielectric media in the case of electrostatic fields and the boundary conditions between two magnetic media in magnetostatic fields. Now if you combine those two, then we are going to get here the boundary conditions in the time varying fields or electromagnetic fields are to be obtained. So in order to derive all such boundary conditions, we are supposed to know what actually linear, homogeneous and isotropic medium and what are the different characteristics of the respective medium, and followed by what are the constitutive relations and all. Now we are going to learn. So conditions at a boundary surface. In order to derive boundary conditions, we are supposed to consider two different boundaries or two homogeneous boundaries. Hence, the concepts of linearity or isotropy and homogeneity of a material or medium still apply for time varying fields. In a linear or homogeneous and isotropic medium characterized by sigma, epsilon, mu, where sigma is given by here conductivity of the material and epsilon be the permittivity of the material and mu be the permeability of the material. As we know that epsilon naught and mu naught, permittivity of the free space medium is given by 8.854 into 10 power minus 12 farad per meter, and mu naught is given by 4 pi into 10 power minus 7 Henry per meter. Now depending upon these two and along with the conductivity sigma, we are defining there are three constitutive relations which are existing here. D equal to epsilon into E means electric flux density and electric field intensity are related as D equal to epsilon into E. Similarly, Along with the polarization, the D can be expressed as epsilon naught into E plus P. This is given by here D, and P is the notation for the polarization of the material. Electric fields. Then a similar analogy which is in magnetostatic fields, nothing but D in electrostatic fields where B in magnetostatic fields. D stands for here electric displacement or electric flux density, whereas B is magnetic flux density. D is measured in coulomb per meter square, and coulombs means generally electric charge can be measured in coulombs, whereas magnetic charge or magnetic flux can be measured in Webers, and flux density is Weber per meter square. Then P equal to mu into H bar. Okay. So mu, epsilon is nothing but mu in the magnetic fields and E is H in the magnetic fields. Electric field intensity as E and magnetic field intensity as H. And mu naught into H plus M. So here mu naught into H is given by B and mu naught into M means this M is the notation for the magnetization of the materials in the magnetostatic fields. And another relation, conduction current density along with the convection current density, we combine the total current density is given by J equal to sigma into E plus rho V into U. Sigma into E is said to be conduction current density, a mathematical equation, and rho V into U be the convection current density, mathematical relation. So these are the three constitutive relations which are interdependent relations or given by D, B and J. Electric flux density, magnetic flux density and current density. Next, for time varying fields, the boundary conditions. Electrostatic fields boundary conditions are derived as E1t equal to E2t and another relation D1n minus D2n equal to rho s. First, in the electrostatic fields, E1t equal to E2t and another relation as D1n minus D2n equal to rho s. If the region is free of region, means charge free region. If rho s is equal to 0, then D1n equal to D2n. Okay, so these are the two boundary conditions which E1t equal to E2t and D1n equal to D2n are the two boundary conditions which are to be derived in the case of electrostatic fields. And similarly, two boundary conditions which are to be exist in the magnetostatic fields are H1t minus H2t equal to K B1n minus B2n equal to 0. If K equal to 0, then H1t equal to H2t and B1n equal to B2n. So from these two relations, tangential components of electric fields E1 and E2 are continuous across the boundary, and normal components of electric flux densities of the mediums 1 and 2 are the continuous across the boundary. Now from these two relations H1t equal to H2t and B1n equal to B2n, we can say that tangential components of both the mediums of H1 and H2 are continuous across the boundary, and similarly normal components of the magnetic flux densities are continuous across the boundary according to if the region has a free current distribution region. Hence, means if K equal to 0, then H1t equal to H2t and B1n equal to B2n. So from these two relations and from these two relations, we have got the boundary conditions for the time varying fields or electromagnetic fields are given by here E1t equal to E2t, or if you want to express that in the form of vectors E1 minus E2 into AN12 equal to 0, H1 minus H2 into AN12 equal to K, and D1 minus D2 into AN12 equal to rho s, and B2 minus B1 into AN12 equal to 0. So either of the four equations we have to say for the conditions which are exist in the boundary conditions which are exist in the electromagnetic fields or time varying fields. So the boundary conditions in the time varying fields means we need to tell these are the four boundary conditions. Now for a perfect conductor means according to the ideal definition of a perfect conductor, sigma to be is equal to infinite. Means for a perfect conductor, sigma equal to infinity in a time varying fields. Now, E equal to 0, H is equal to 0, then J equal to 0. Now, Y E equal to 0 means according to the for a perfect conductor case, sigma equal to infinity. If sigma equal to infinity, according to the conduction current density, we know that J equal to sigma into E. Then from this, if you evaluate the equation for sigma, then that is, or from this, if you're going to evaluate the equation for E, then E equal to J by sigma. Now, if you substitute sigma by infinity, J by infinity, now something by infinity, which is equal to 0. Hence, E equal to 0 according to the perfect conductor in a time varying fields. If we are assuming sigma to be infinity, then E must be equal to 0. If E is 0, H is also 0. Why? Because as we know that the relation between these two, E and H, according to Faraday's experiments, del cross E bar equal to minus dou B bar by dou T. Right? So, del cross E bar equal to minus mu into dou H bar by dou T. Okay? So, if E equal to 0, this total term tends to 0. If mu is also 0, then H bar equal to 0. So, E is 0, H is 0. According to that, J is also 0. Why J is also 0? J equal to dou D bar by dou T. If E is 0, D is also 0. Why D 0? D equal to epsilon into E. Then if E bar equal to 0, then D is also 0. Similarly, B 0, then ET 0. Okay. So these are the boundary conditions which are to be existed in the case of electromagnetic fields. Right. So what we have learnt in the case of this particular lecture means firstly, we have learned what do you mean by displacement current. From that, we have evaluated the equation for displacement current density, that is dou D by dou T as JD. And there is one more term we have learned is inconsistency of Amperes Circuit Law, that is which is to be adding in the case of Amperes Circuit Law, that is del cross H bar equal to J plus JD. This is the law which is called as modified form of the Amperes Circuit Law, or simply called as Amperes Law for time varying fields. And after that, we have discussed finalized forms of the electromagnetic waves or time varying fields. Then we have learned the different boundary conditions which are to be evaluated in the case of time varying fields or electromagnetic fields. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.